So in this next part of the question, we are going to be dealing with bacteria. And according to part B, in one of the models that the scientist has came up with, we are supposed to be working on the growth rate of the bacteria. And according to the question, this growth rate is proportional to the number of bacteria. And according to what the question says, the number of bacteria is represented by N, and the time in days is represented by T. So for this part of the question, if I were to look at dN dt as the rate of change of the population of the bacteria, that means, according to what the question has described to us, there is a rate of input, which is described to us as the growth rate of the bacteria. It is going to be proportional. I'm going to use K as the constant of proportionality. So K times of N, K times of the population size of the bacteria. The question didn't really mention about the rate of output, so we are going to assume that the bacteria will not decrease as the days goes by. So the rate of output is going to be equal to 0, which means that dN dt is going to be the rate of input minus away the rate of output, where dN dt is going to be just Kn. And because we define the rate of input and rate of output via our positive and negative sign that we try to put here, so this K that we have defined here should be a positive constant. And what we are going to try do is to try to write down the differential equation which we have just done, and we are supposed to solve this differential equation so that we do a projection of the number of bacteria in 50 days time. So let's try to see what we can do for this equation first. If you have to look at the information that is given to us by the question, it did mention to us that at time t is equal to 0, the bacterial count is 5,000. Let me write that down. So at t is equal to 0 initially, the number of bacteria is 5,000. And the question also mentioned that the growth rate during this moment is 200 per day. So growth rate will be dN dt. Okay, because the growth rate is directly dN dt. So dN dt is equal to 200. And I guess this piece of information is actually useful enough for us to sub it into this equation here to find the unknown K. So let's do it, which means that if I were to sub it into here, 200 is going to be equal to K times of 5,000. This tells us that K over here is going to be equal to 1 over 25, which means that dN dt is 1 over 25 times N. And let's try to solve this differential equation so that we can do that projection that the question requires us to do. We want an equation that is of N and T, okay, without all the differentials here. So this is a first order variable separable differential equation, and according to how we have discussed it on the Achevas TV theory part of it, we are going to try to divide this across to the other side, which will be giving us a 1 over N. dN dt is equal to 1 over 25. And integrating both the left and the right hand side with respect to t. On the left hand side, it will be reduced to this. And on the right hand side, it is still going to be continuing with a differentiation with respect to t. So if I were to factorize out 1 over 25, we are basically differentiating 1 with respect to t. For what we have here, this is going to be ln modulus of n is equal to 1 over 25t. Let me continue here. Let me try to make n the subject. So modulus of n, this is equal to e to the power of 1 over 25t, which means that n is going to be, oops, I forgot the arbitrary constant. So in the previous question, I have used a, so let me just go for a b for the arbitrary constant for this. So here plus b, so this will be e to the power of 1 over 25t plus b, and I remove the modulus, so I'll have a plus or minus here. I can also write this as n to be plus or minus e to the power of b, e to the power of 1 over 25t. And I think it is way more convenient if I were to represent this as another arbitrary constant, which I'm going to call it c. So it will be c e to the power of 1 over 25t, where this c here is this plus or minus e to the power of b. Let's try to solve for c because we have this set of information. We know that when t is equal to 0, n is equal to 5,000. So n is this c e to the power of 0 is equal to 5,000. E to the power of 0 is 1. So this tells me that c over here is in fact 5,000. So with this, we can now write down an equation that is rid of all the differentials. It is the solved version of this differential equation. N is equal to 5,000. C is 5,000. E to the power of 1 over 25t. And we are going to make use of this to do the projection. The question requires us to find the number of bacteria when the number of days is 50. So we're going to let t be equal to 50. So when t is equal to 50, that means n is going to be equal to 5,000 e to the power of 1 over 25 times 50. Pressing this into the calculator, writing down my answer in 3 significant figures, I'll be getting a 36900. Okay, this is part B. Let's move on to the last part of this question. Okay, for this last part of the question, we are actually given a new differential equation directly. Let me write it down. We have dn dt is equal to kn, then ln m minus ln n, where it is also given to us by the question that this k and m here, they are positive constants. So let me write that information down for myself also. These are bigger than 0. What we are supposed to do is to try solve this differential equation first. Then we want to give an interpretation of this m over here. Okay, so we don't really know how to do that very last part yet. We need to take a look at the equation before we can decide, how we can sort of like interpret m in the context of the question, definitely. So let's just try to solve this differential equation. We are looking at this with n being the variable and t being the variable. It is also, once again, a first order variable separable differential equation. So I'm going to bring this entire expression that consists of n dividing it across to the other side to give me a 1 over, we have a n, then ln m minus ln n dn dt. This is equal to a constant k. And if I were to integrate both the left and the right hand side with respect to t, on the left hand side, it will be reduced to this 1 over n ln m minus this dn is equal to k is a constant. I took it out of the integral, and we will be just integrating 1 with respect to t. And I think this is easy, right? Integrating this is just going to be t. But for this can appear a little bit confusing. So what we need to remind ourselves is that this m over here is a constant, which means that ln m is a constant. And in order for me to integrate this, we are going to make use of the ff prime, okay? Which means that for this, if I can just treat, for example, fn as this expression over here, which is a constant minus away ln n. And f prime is going to be equal to minus 1 over n. Okay, hopefully you will be able to see the version of ff prime in this over here, like how we have discussed about it, integration technique on the Achevas TV. So if I were to do the same for, if I were to try to re-express this into the format so that it is easier for me to recognize the ff prime, it will be a minus 1 over n. Okay, that's why I have a negative outside to simulate this. And for fn, it is going to be the denominator over here. So it will be 1 over this ln m minus ln n. So dn, this is equal to k integration of 1 dt. So integrating this will be minus ln modulus of this minus ln n. It is going to be equal to kt plus an arbitrary constant. Okay, how many arbitrary constants have I used? I've used a, b, c. Let me use d over here. Okay, so we have this, which means it is going to be a ln modulus of ln m minus ln n. I think notation-wise, by itself, right, it is already a little bit challenging. And this is actually an exam question, so I guess the students who are going to be doing this probably feel a little bit intimidated and uncomfortable by so many logarithmic function written here, okay? So this is going to be equal to minus kt minus d, and removing this particular ln, it is going to be modulus of ln m minus ln n is going to be e to the power of this, which I'm going to break it up into e to the power of minus d, e to the power of minus kt. Okay, now we have this, let me remove the modulus, leaving me with this minus ln n is plus or minus e to the power of minus d, e to the power of minus kt. And I'm going to do one last replacement. I'm going to replace this here by another arbitrary constant for the sake of convenience, dE. Okay, E is a bit, because there's already an E here, but I'm going to just go for the uppercase E. Okay, so E, which is an arbitrary constant, where E here is this plus or minus e to the power of minus d. Okay, so this is the solved version of the differential equation. Okay, it is not necessary for us to always try to make n the subject or t the subject. Once it's solved, it is solved. Once the differentials are gone, it is considered solved. So this will be my solved differential equation, especially when the question just asks for it to be solved, not to be expressed in any specific ways. We want to hence give an interpretation of m in the context of the question. And I think this can be potentially a bit difficult because it's a bit open-ended. So for what we are looking at here, there are a few things that, okay, not exactly a few things, but there's one thing that comes to my mind that I think we can try to move in that direction, which is, there are two things actually. One is when t is equal to 0. The other one is when t goes all the way until infinity. So when t is equal to 0, I don't think I can analyze anything much for this, because when t is equal to 0, this will become 1. Basically, ln m minus ln n is equal to an arbitrary constant, which we do not know. I think one good way for us to try, other than letting t be equal to 0, is letting t goes to infinity. Let me show you what I mean. That means when t goes to infinity, okay, we are just exploring and trying, okay. When t goes to infinity, we can see, because k is a positive constant, which means that when t goes to infinity, this entire expression will turn to 0, right? It will become so negligible, which means that when t tends to infinity, ln m minus ln n is going to tend to 0. And this tells me that m is actually equal to n. These two are the same. Or this tells me that n is equal to m. M is a constant. N represents the number of bacteria. So what is this telling me? This actually gives me a good interpretation of what m represents. This tells me that m represents the number of bacteria in the long run. Let me write it down. So therefore, m is the number of bacteria when t tends to infinity. So in the long run.